Welcome back, folks. We just wrapped up talking about what I call a stupid unit of energy, the watt hour or the kilowatt hour. And I promised you there was one stupider. And then my daughter reminded me that maybe it's the stupidest, but it's the last one we're going to talk about. And I'm sure there's a stupider unit of energy out there. Actually, I know there are. Some of the imperial units get kind of funky. But it's the one that we're going to talk about as it relates to electronics, because you're going to find it on batteries mostly. When you're sizing a battery, how much energy do you need in a battery? You may run into, actually, there's a very good chance you'll run into this unit of energy. So I usually have props for this one, and I ask for props from you because a lot of you walk around carrying these battery packs for your cell phones. Okay, I'm waiting on my green screen to come in, so I've got a blue sheet behind me to make this magic happen, and my battery pack is blue. I'll get a picture for it pasted in there in a little bit. But this is one of those USB chargers that you use to charge your cell phone when we're on campus and you don't have a plug or anything like that. And this one has nice branding from IEEE USA. I'm the student branch advisor, and I work with IEEE Connecticut section as well. So ask me about that in the live show if you want to talk about the club activities that we do and some of the things that IEEE does in Connecticut as well. But I usually ask you for one of these, and I just go with it because it has some information written somewhere, and all of yours probably have information. I haven't found one that doesn't yet. When I just pull one out of your bags when we're in the classroom, it has information on how much energy you can store in here, and it's in the stupider unit of energy. So let's go ahead and take a closer look on some of this stuff. Okay, so I'll get myself down here. Stupider is actually a word. It's not more stupid, although stupider just sounds funny to me. Perhaps I should be more articulate. But why should I start now? Okay, let's see. Whoops. Let me get my picture here. So this battery pack, here I got a nice picture of it so that you can see it up close and personal. Just looks like that. Okay, and I took a good picture of the label as well, if I can find the picture of the label. Okay, and the picture of the label looks like this. Okay, can you even? Yeah, I think that's legible. Let me zoom in a little bit for you. Let me zoom in and make that better. Okay, nice and big, so we can definitely see what's going on there. Okay, so we're interested in the energy capacity for this thing, and it says right there, capacity. And look at the unit. It's in milliamp hours. Okay. Well, watt hours were stupid enough, but amp hours are just worse. And furthermore, it's in milliamp hours. So I notice a few things here. It's in amp hours, which is just strange. And it's in milliamp hours, but it's 4,400 milliamp hours. And that always bugs me because that's not proper engineering notation. They're using the SI prefix milli, but I have more than 3 digits to the left of the decimal point. And why in the world would you do this? And the answer is an engineer didn't do it. I promise you a business major did it. 4,400 milliamp hours sounds like a lot, right? It's 4,400 of something, whereas 4.4 amp hours is not as exciting, but it turns out they're equivalent. Okay, so it's a marketing thing, and you know, I guess we should let the business majors have a little fun once in a while. Anyhow, okay, and amp hours is just a bridge too far for me as far as units of energy goes, because an amp is a coulomb per second, right? So let's think about what an amp hour is, and the alternate unit for amps, it's a flow rate, is a coulomb per second, and I'm going to multiply by hours. Well, at least with watt hours, it was a joule per second, and even though these times didn't cancel perfectly, they were both times, and we ended up with some measure of energy in the numerator. Here we're going to end up with a measure of charge. So talk about how much charge you can it's not, it doesn't work out to an SI unit, but nonetheless that's what we're looking at. Okay, so maybe pull your power bank out and look at its capacity. This one's pretty small. I got it for free. It had IEEE branding on it, but some of the larger ones get quite big. What this is telling me is how many amps I can draw from this power bank for some period of time. So the assumption is that you're drawing it at 5 volts. Okay, and if I want to convert back and forth between amp hours and watt hours, then we got to think about the fact that power is equal to V times I, right? So if we're thinking about units, this is watts equals volts times amps. Okay, so if I want to get to how many watt hours this particular power bank is, a lot of them listed, this one didn't, also in watt hours, we can simply multiply amp hours by volts of the output, and we're going to get our energy in watt hours. Okay, so let's see, we have, I'm going to use 4.4 amp hours. Okay, and this is a measure of energy. 4.4 amp hours, and it's 5 volts. Okay, so that ends up being 22 watt hours. Okay, so I can get 22 watt hours out of this battery. I'm certainly not running my bouncy house off this with that little energy. Not going to happen. Okay, so larger batteries also have this. So there's a conversion between the two. It's just looking at whatever the voltage is. Okay, you got to add that voltage in. A lot of the times batteries will be rated for a particular voltage. So I have another battery that I want to look at. So let's scroll down here and let me get you. I don't have this one. It's in my office on campus, and I can't get anywhere near campus. So we're going to have to deal with having a picture of it instead. I run a small robot off of these. It's a pretty common battery. I think you can even buy them at some big box home improvement stores, which will remain nameless. But it looks something like that. And if you look closely at this one, again, it has its capacity listed in amp hours, and it's rated for 12 volts. So the energy in this particular battery, you know, on a data sheet, you're going to see it as 5 amp hours, but now you're smarter, and you can say 5 amp hours times 12 volts, and you're going to end up with something around 60 watt hours. If you could see them side by side, this one is physically bigger. So, you know, the fact that it has a larger capacity shouldn't be too much of a surprise. The chemistry is a little different, which you can talk about energy density. This one that's going to disappear into the background. This one is lithium ion. I believe it's lithium ion. Yes, it is. And the one that you're looking at up here on the screen is a sealed lead acid battery. So sealed lead acid tends to be less energy dense. It's a much heavier battery, and it's bigger than the lithium ions. This one is a little more complicated to charge. You need some electronics to treat this one right. That one up there, I can hook up to the power supply, and as long as I set the settings right, I can get some charge in it. So it's simpler to charge, it's cheaper, but it's heavier, and it tends to be bigger. Okay, but in this case, it has a bigger capacity. It's holding 60 watt hours. Okay, so what do we do with that, and how is that information useful to us in any way, shape, or form? So let me grab an example here and say, how long will this battery last, right? Because how long will this battery last? Okay, whatever you're using this battery for, I'm running a robot to try to drive around the hallways of the building and stuff like that. So if it lasts 30 seconds, I'm in trouble. If it lasts 48 hours of continuous use, I've probably made it too big and it's way too heavy. So there's some middle ground to be struck. But we want to know if we connect something to this battery that's going to draw 1.3 amps from the battery, how long is it going to last? Okay, when does it discharge? And again, I want you to follow units. In all of stupid units of energy, all of these things, everything we do in class, everything you do in your practice of engineering, I want you to pay attention to units as much as possible because they're going to prevent you from screwing up and doing a calculation wrong or something. If you're comfortable with the units and you see how to manipulate them, you can kind of guide yourself through how to work these problems. So we've got 5 amp hours, right? And we want to say how long will it last, so a unit of time. So we want to get down to just hours. Okay, so we want to say time is equal to 5 amp hours. And if we want to get rid of amps, we have to divide by amps, right? So we get 5 divided by 1.3 amps. Now amps is going to cancel amps. Get you a different color for that. Diagonal lines are tough. Okay, amps are going to cancel amps, and I'm left just with hours in the numerator. So 5 divided by 1.3, and that's going to tell me how many hours the battery is going to last if I'm drawing 1.3 amps from it. So 5 divided by 1.3. 3.8, let's call that 3.85. Okay, a little bit of rounding between friends. A little bit of rounding, not a lot of rounding. 3.85 hours. Okay, now if I needed to convert it to minutes or something, I could do another unit conversion over here if we wanted to, but we don't need to. Okay, so that's a reasonable amount of time for a battery to last for the application I mentioned, but that can change depending on what's going on. Okay, so if I wanted the battery to last 24 hours, we can play the same game. So how much current can we draw? Can a circuit draw? From this battery for 24 hours of use? Okay, so maybe we can change our circuit so that it will work with this battery, but we have to put a requirement on it. We have to say the circuit shall draw, X amount of amps, or lower, right? We can always draw lower, and we can play the same game. We can say how much current can we draw? So current is I, right? From our 5 amp hour battery, if we want it to last 24 hours. Okay, and we'll do that same kind of calculation. 5 divided by 24 is, okay, so here's where I wish this Windows calculator did a little engineering mode. I am going to find an emulator that works because you should get used to using the tools you will be using for class. But this looks like 208.3 milliamps to me. Okay, so if I have a circuit that draws 208.3 milliamps, then it's going to last 24 hours. Now, it's a little more complicated with that. Battery chemistry gets funky, and the voltage starts to decline, and regulators are going to kick off and things like that. But a good estimate of how long this will last, drawing 208.3 milliamps, is for 24 hours. All right. So it's a stupid unit of energy. It's not a unit of energy. It's almost a unit of charge, but it has that same problem with the factor, since we have different hours, different units of time in the numerator and the denominator. So we have that factor of 3600 in there as well. All right, but you will see it on batteries. You'll see them on everything from batteries like this one. You'll see it on batteries like the one that I have up there, and just about any battery you can go buy from a reputable dealer is going to have the capacity labeled either in amp hours or in watt hours. And hopefully you're comfortable switching between the two. Okay, so a little more web work problems on that, and we're going to start the next section of the course. Okay, hopefully this has all been a little bit of review, but we're talking about some things in new ways and how to use it in different ways. So I think it's worth getting everybody going in the same direction. So hopefully you're feeling that. We're going to start building more complicated circuits next. And we still have 2 more laws that we need to get to. We've talked about Ohm's law. That's the first fundamental law of circuit analysis. There's 2 more that we have to get to. But before that, we have to learn about different parts of a circuit, how to build more complicated circuits. So that's where we're headed next. Stay tuned and good luck, folks.